And this is a very low-level intro to the GNU Toolchain. So let's start first. How many people are now using the GNU Toolchain, just by show of hands? 1, 2, 3, 4. Okay, only about half, a little less than I was expecting. How many people have used other toolchains? Pretty much the same set. Okay, well in that case then this is actually going to be new information to more people than I thought it would be. However, those who have used it, keep me honest. And let's see. There's also, for me, there's an intro to this computer. I've had it less than 24 hours. So if anybody knows how to use an HP Pavilion, please tell me how. All right. So you've seen the splash. Basically, a tool chain is used for compiling. Why do we compile? Because if you're using scripting, you're limited necessarily by speed. Compiling is almost always going to be faster with any form of foreseeable hardware. But compiling is adjusting your programs, customizing them to the particular target. Scripts pretty much run anywhere. They run it intended for use at human speed. Compiling, you're going to run something, you want it to run several times faster than you can. Hopefully several thousand times faster than you can. And that's usually easy to accomplish. Rather than you, however, having to know the peculiar properties of the computer, we use toolchains to do it. The toolchains know the applications, they know the details between whether it's an Intel processor, whether it's a Power PC, whether it's a MIPS processor, etc. I'll be talking today only about single CPU compiling, but one other use for compiler is to actually distribute processing. And if somebody wants to deal with that, we'll maybe do something on that in another presentation. By the way, since this is an introduction, especially those who've used them, if you want to interrupt with questions at some point, we can get some discussion going on any of these. All right. Part of using any tool chain is to take advantage of what's called a software life cycle. Let me move that down too far. Let's get that back up again. When you, there we go. Okay. The benefit of software is that you can change it. The bane of software is that you can change it. So the purpose of a tool chain is to manage that, give you the benefits of changeable code without giving you the problems. And back in the 60s, as well as again in the 80s, keeps getting repeated, the various organizations that have analyzed it have found what the historically optimal ways are to generate software. How many people read the book Software Engineering by Deming? I think it was by Deming. Actually, it wasn't by Deming, it was by Hand. Anyway.
No, I think Brooks.
No, not Brooks' Mythical Man one. The guy, I had his name a minute ago. Anyway, mostly, anyway, how many people read the classic textbook Software Engineering? Okay, 1 person, 2 people, 3 people, good. All right. In it, he proposed principles that really haven't changed regarding that it's not just the number of lines doesn't mean much, but complexity, locality, flexibility, these do.
I think you're talking the author is Pressman?
No, it begins with an H because he's also known for the metrics that
Halstead or Halstead or something.
Halstead, thank you.
Yeah, that's the guy.
I kept confusing him with Hamming in my mind. Halstead. He pushed for metrics. Anyway, so while there's multiple ways of slicing the pie, the one that seems to be becoming most popular now, the terminology changes, is what they're now calling plan, build, run. If you've heard this before as waterfall, it's the same thing. The idea basically is always iteration. One thing that IBM found in the 1960s, AT&T found later, is that when you're doing software, you're almost always doing something you've never done before. So you don't know how long it's going to take. And that's contrary to a lot of what the business people want, but it's the truth. So what they found by looking at successful projects was that you make your best estimate as to how long it's going to take you to complete it. You start doing it. And as you do so, you revise your estimates. When your estimated time of completion exceeds your estimated time of planning by 2/3, both of them came to the conclusion that meant you probably needed to go back to the drawing board. In other words, if you estimate it's going to take 3 months of planning, 2 months to implement it, and historically then you get a month of debugging, then and you start into it and you find out, oops, we're 2 months into it and we're not going to get it done in 3 months. Well, at that point, you want to now go back and, or rather, not so much on that, when you start implementing it, you get into it a week and you find out, oh, we hit something hard, we're not going to get this done in 2 months. So instead, that's the time to go back and, as they say, go back to the drawing board, replan that portion of it. But those iteration loops are what make software production economical historically, whether you call it plan, build, run, or whatever you call it. Okay, so the plan is to have specs. That's whether there's hypo, UML. Specs, by the way, includes test programs. You want to think about testing before you've written a first line of code. I assume all of you have heard that many times before. How many people actually have written more than 50% of their code with tests before they wrote the code? Okay, one. Okay, yeah.
I'm a junior on the team, I don't get a choice.
Okay, good. Well, actually, that's good that the test code's there first. That's if I restrict myself to my own code, I'm exceed that. But unfortunately, that hasn't usually been allowed by my employers. When they have, by the way, it's resulted in very fast code, produced much more economically, more reliably, and with longer lifetime, including some that was produced at Chrysler 10 years ago and is still being used today. Okay. So then you try to build it, and it's in this build section that the GNU Toolchain fits, and most of the popular toolchains out there fit as well. Mind you, GNU does have is associated with some components in plan and run, and some of the things like WebSphere, if you want to call them a toolchain, they have much more in the plan and run than they do in the build. So that becomes what you call a toolchain. That's different manufacturers are going to give it different definitions. But the GNU Toolchain was originally intended by Richard Stallman. I assume everybody's heard of Richard Stallman? Almost anybody not heard of Richard Stallman? One person, okay. Well, basically, Richard Stallman was the guy who was behind the GNU, GNU is not Unix project. His goal, mostly implemented by AT&T, was to put together a Unix, what basically became the model of most of the open source projects today. There were open source projects before him, but a lot of the software open source projects were basically modeled on his original GNU idea. And what you see on what's commonly called Linux today, and a large portion of what's in BSD also, is actually GNU, most of the basic utilities. Okay, so anyway, when you have your specs, you write source code and build it, test it. The GNU helps you with that. If it, until it passes your toolchain test, it stays in build. Finally, you get something you think is runnable, you try and run it, oops, somebody missed a spec, it's too expensive, some unforeseen requirement occurred, or just plain a change. Okay, update the specs, go through it again. Okay, all this I'd say, and any companies here that are also using plan, build, run? How many? Okay, 2, 3, all right. But what they call it by different names. but it all works out. Okay. Now, that's the macroscopic view. Toolchain actually remembers in the development in the building, and so, let's see, did I miss part of that? Nope. What I missed isn't that significant. Okay. In the development cycle, you still have the plan, but what you're depending on your toolchain for is to give you the debugging help. That would be the syntax warnings and errors, to do the packaging, or at least to help you with the packaging, to help you with the testing. GNU has a variety of tools for these to add tests. So you start with the specs, you edit the source, you build it, you test it. So you're spending a lot of time in this triangle. Ideally, you want that if you have good feedback, you'll minimize the time, and you'll actually end up spending, the goal is to spend the least amount of time possible debugging after you release. You want to release code that's reliable and easy to change and doesn't break. Customers don't like broken code, especially if it's embedded. Okay, all right. So we test the failed test, you debug. Most of this is just terminology, but a toolchain, such as the GNU Toolchain, provides the pieces that fit in these four squares. End up, of course, with working code. Okay. Slight more detail here. Come on. You have to learn the timing on dragging with this thing. All right. The GNU Toolchain, like most, has the has compilers, GCC, which is their basic one. It's actually EGCS, which is a generic parser that is configured then to handle C code, C++, Fortran. I think they've actually got about 20 languages now. Anybody here using GCC for other than C or C++? Okay, one person. Two persons. Okay, what are you using it for? Fortran?
I'm strictly CC, not C++.
Oh, okay. Strictly CC. All right, you, what were you using for besides C or C++?
Well, we weren't actually using compiler, we were using pre-compiler.
Okay, precompiler, yeah. That's one of the tools, is the precompiler allows you to alter the source, which is a requirement of the ANSI specifications for both C and C++, and GNU supplies that as well. GCC is their single point of entry. A lot of GCC calls other tools, not always contains them. All right. When you compile code, other people have compiled code that you want to take advantage of. Nobody wants to rewrite the wheel every time. So compression algorithms, for instance. The experts have generated some very good ones, so you don't need to generate your own compression tools these days. Likewise for handling list structures. So for that, libraries. In the toolchain, the GNU Toolchain world, they tend to have two types, .a, .so. .so is shared memory. .a actually got its name from assembled, and it is the archive of object files, .o files. AR is the GNU Toolchain archiver. It allows you to pop files together. How many people here are familiar with tar? Especially those, everybody, wonderful. tar is the tape archive. Archive was first, 1960 something or other. tar came later. And it was because there are differences between using a tape drive, it's serial access as opposed to memory. they made a modification, called it tar. Tar ended up becoming very popular among people who never saw a tape drive. How many people here have used tar in the last week and have never seen a tape drive? 1, 2, 3, 4, 5, 6. Okay. Yeah. Some of us still remember tape drives. I'm sorry, go ahead. I'm sorry, go ahead. What are you going to say? Okay, all right. And by the way, if you're familiar with Java, jar actually also gets its name the same way. Okay, so you have objects. Objects are a single file that's been compiled. Libraries are collections of objects, and depending on the protocol that's used, such as ELF or what's called a.out, they will have additional information besides the .o. In particular, they will have a symbol index, so that when you go to combine the libraries, it has the offsets or information to find the offsets into the objects for each of the variables. So when the two libraries are combined, it can replace, as it loads it, the pointers to the calls in other libraries. That avoids the problem in memory of having to have special jump tables all over the place, which makes virtual addressing very, very hard. But if you know anybody that ever used to use an IBM 360 or a PDP-11, ask them about it. Okay, so it also, by the way, allows you to have the linker, LD, for GCC, also includes a versioning protocol. How many, I assume everybody here has seen the libraries that end in -1.0, -2.1, -3.0, and most of them are symbolic links. Okay, that is a protocol that GNU established. As far as I know, they were the GNU set many standards associated with their toolchain. One of them is the numbering scheme for the libraries. And the linker will walk back to find compatible libraries. But it allows you, by the scheme, to have multiple libraries, multiple sets of libraries, on the same machine. You have older code that won't work with the newer library. It was broken by the newer library. On with the GNU Toolchain, that's okay. You keep a copy of the old library around for the legacy code that needs it, and use the new code with the new libraries. Gives you the new features. So that's the GNU linker, available also through GCC-L. Most of these are available, like CC is available through GCC-C. Okay, so we have as okay. Also, GNU has a lot of docs, a huge amount of docs which are helpful, and makefile. Is there anybody here who hasn't used a makefile? Okay, everybody's used a makefile. Good. Anybody? By the way, out of curiosity, how many people use makes more often than ant?
Than what?
Ant.
Never used ant.
Okay, about 2/3. All right. Yeah, make is wonderful, and that's also out of the GNU Toolchain. Basically, the compilers take source code. In the case of CC, it's block structured. Make is a dependency script. It looks at what it resolves dependencies. So it isn't just strictly related to building source code. I've used Make for verifying security systems, because it will verify that things that need to happen in order have happened in order. If something was interrupted, either because of hardware failure, network dropout, whatever, Make is a beautiful way to confirm that sequences have been met. Okay. The notes on here, by the way, correspond to, well, you can see. You start with the source, compile it. There's a feedback loop there. The compiler gives you the syntax warnings and the errors. Anybody here remember lint? Okay, a few people. Compilers in the very early days didn't provide you with the the syntax checking. You had to use a separate program for that. GCC, the GNU Toolchain, and by the way, there's still some tools that have that. Anybody here program a BlackBerry with the BlackBerry Toolchain? You had to handle your syntax checking separate, and it was a separate, also a very expensive piece. They didn't give that away free. You get the syntax checking built into the GCC. Some people complain that the C++ gives too much information, but it's essentially self-indexing, so you can pick out, you can filter for what you need from it. And my own experience, it's better to have too much information like you get from the GNU C++ compiler and filter it. If something goes wrong, you can always find it.
Right,
Yes?
syntax checking, I mean, the compiler is doing syntax checking all the time. It's the best practices and that kind of a thing that Lint was doing. It was making sure that functions returned what they said they were going to return, and that arguments were what you stated them as. That's what Lint would do.
Well, GCC now combines that. It
Yeah.
gives you that information.
Yeah.
Go ahead.
Yeah, I just wanted to add, if you read some of the old original Unix papers from the Bell System Technical Journal,
Mhm.
they
Nice little
mentioned
demon on the
that
cover.
they liked to separate these out because they wanted to keep the tool simple, be able to assemble a pipeline and use it for different purposes. But also in those days, they didn't have enough memory in systems, so they resorted to that. Well, and GNU came much later, and there's an old joke that Stallman couldn't write code in anything less than 64 megabytes, even if he had to save his own life.
That could be true. Yeah, I think Stallman was on the scene in the early 1980s.
Yeah, I'd say mid-80s, yeah.
And he was very, the software community benefited greatly from what he was doing. I mean, at the time I got from the U.S. District Attorney a letter saying that IP addresses were classified and wanting a list of everybody who had access to IP addresses. As an ARPANET liaison at the time, one of my monthly responsibilities was to distribute a list of IP addresses to anybody who wanted them. This was before DNS, by the way. So I was thinking of sending the District Attorney of the United States a copy of the phone book.
Yeah.
Oops. Don't look at my password.
Star.
Uh,
Now we know.
Good password.
And now we know.
It matches everything.
Yeah.
Okay, so we get the syntax, you get from the compiler, the objects, the archiver puts them together and indexes them. Depending on if you choose some A dot out, you have to explicitly do the indexing. It's just another command in the make. You can get third-party objects, third-party libraries, and docs. It's not actually part of GNU, but it's associated with it. There's also doxygen and a lot of documentation tools. Has anybody here heard of doxygen? Is there anybody here who hasn't? Oh, about half haven't heard. Okay, what doxygen is it is a compiler that generates, how should I put this? Okay, it generates hierarchical documentation structures based on its own source code. It also includes a syntax analyzer that can handle C++, C, and a couple other languages, Java, etc. You can, with doxygen, you can write what you mean, as they say it. So what you see is what you mean rather than what you see is what you get type of compiler. And it's very well optimized for generating automatic documentation from source code, especially C and C++ and Java. Yeah, those who are familiar with doxygen, anybody familiar with JavaDoc or PearlDoc? Okay, anybody not familiar with at least one of those, PearlDoc, doxygen, or JavaDoc?
What's familiar? I've heard of PearlDoc.
Okay. I don't remember the precise sequence. I think PearlDoc was the first one, which was intended for Perl code. Then I think JavaDoc followed on it, I think doxygen was the next one chronologically, which was where they adopted a similar structure for C and C++ code. And then JavaDoc, when it came along, did the same thing for Java. Okay, I'm throwing out these names. And technically, doxygen isn't part of the GNU Toolchain, but it's associated with it well enough that probably is. Okay, and we're actually ahead of schedule at this point. I handed around there was a USB, if anybody wants it, that I should have mentioned that earlier, with the code if anybody wants to try following along. Otherwise, I'll just show you on the screen. Very simple.
Which will install a keylogger on your laptop at the same time.
Pardon me?
Which will install a keylogger onto your laptop once you plug it in.
Almost. It won't install the keylogger now. What it's actually going to do is install a bot, which the next time you go to the internet, it'll wait for you to enter some, I don't know, pins or something else, and then it'll only log that and send it to me. So, yeah, no, I didn't want to waste just putting a keylogger on everybody's machine. That's anybody can do that. I assume everybody knows what a keylogger is.
Yep.
Okay. By the way, I've done security for years, so and part of that, by the way, has been breaking security. One of my funnest jobs. How many people here can say that they robbed a bank? Okay. I can. I got paid for it.
That's the idea.
Yeah. It was a
They lied.
test of their systems, and I succeeded. Yeah. Actually, I ended up stealing the money from the account of the bank officer who hired me. I figured, why involve another person? So, under the law, by the way, I had to return the money, and then I got paid the fee, which by coincidence was equal to the money I took. But I had to return the money first under the law. Pardon me?
Should have picked a bigger account.
Should have, but that wasn't, the negotiated the amount as part of the contract. All right, so now just a demo of this. By the way, before we go on, any questions? How many people is any of this new to? Okay, 1, 2, 3, 4, 5. Okay, so not everybody's seen this before. Good. Wasn't sure in this audience how many people wouldn't have already seen this. All right. What's the simplest program you can write? All together. Hello world. So what do you think the program we're going to demonstrate is? Right. Okay. How many lines of code are in this, by the way? Just as a guess. Okay. Myself, I'd say about 20, because I count those comments. Part of programming, part of what this is about, clarity matters. Code is easy to write. Comments are hard. Comments are what give you reliable code.
You can see the influence of Mr. Halstead, who had as one of his software metrics the ratio of comments to code.
Mm-hmm. I used to work for a company, ProCase, where we set records with reliable code making money. And we had metrics for things going out the door. One was that our code density had to be, could be no less than, I believe it was 7 bits per symbol. In other words, the size of the binary code, which is actually a good, fairly good metric, 5 is the binary compiled code, divided by the number of unique symbols, had to be at least 7 and then the logarithm of that had to be at least 7 bits. If it wasn't that high, it wasn't going out the door because they figured it was coming right back in again. I might add, most companies I've worked for since then have not used that high a metric, and code usually comes back a lot more often. We had nice, happy paying customers and didn't have to waste our time fixing code. We just add features. All right. Yeah, the other thing is, when at that company, by the way, we did our walkthroughs, comments only. Strip the code, just do the comments. Because if you get the comments right, the code is generally easy to translate. It's local, so don't have a problem. All right, anybody think this code's going to work?
No.
How many people, by the way, have written a piece of code that, well, let me ask you a different way. How many people have never written a piece of code that worked the first time? A full program that ran the first time without errors, bugs, nothing. Ah, so everybody here has had at least one program they wrote from scratch and it worked the first time.
Usually people have never.
Right, so if it's never not, then that means it's at least some.
Usually I'm testing as I'm writing though.
Pardon me?
I said usually I'm testing as I'm writing though.
Good. Okay. Well, anybody want to place a bet as to whether this will work the first time?
I'm saying yes.
I don't see anything wrong with it.
Okay.
I don't mean that.
Key thing there. Somebody who's used to programming just said he doesn't see anything wrong with it. Very good. This is the reason for using a tool chain. And that's exactly right. This is, you wouldn't, whoops. It doesn't look like there's anything wrong with that.
Oh.
Exactly correct.
Yeah.
About to learn.
Okay.
We're about to learn what's wrong with it.
Yeah.
Yep, you're about to learn what's wrong with it. That's right.
Includes.
Okay.
Okay.
Lots of options, but the most, GCC assumes C code if you don't tell it otherwise. If you can run lots of languages with it, you can specify with -x, regardless of what the file name is. Otherwise, it will assume based on the file type. But of course, in Linux, there's no requirement for file types. So you can always tell GCC with -x that your code whose file name ends in .c is actually C++ or Fortran or whatever you like. Okay. It also assumes that no libraries need to be produced and an archive is unnecessary, but again, you can tell it to. And again, I'm pointing out what's possible. If anybody wants to see how these are done, we'll do them. I suspect a lot have already seen them. Those who've used it before would have. And nominally it assumes one executable. So now let's see if 2 lines, ostensibly, of code will actually work the first time. Let's see, that's probably not so readable. Let's see if I can blow that up. Okay. Everybody see what it found that none of us did? Now note, by the way, this is a warning. Anybody want to tell me what the difference between a warning and an error is and an information?
You still got executable code.
Yeah,
Still
okay.
generates the code for you.
Okay, still get executable code. Key thing is, a warning is telling you the compiler made an assumption. The compiler, the tool, the library, linker, whatever, it made an assumption. You have to check if the assumption it made was correct. In this case, it's telling you that it saw a function. You didn't name it. You didn't define it. It didn't know what it was. It's assuming, however, that it's going to appear from somewhere, doesn't know where, and that it must have an integer as the implicit declaration.
You missed your,
Go ahead.
STDIO
Bingo. Okay, and he's already got the cure, which is exactly correct. So,
Or you could have just defined it yourself.
could have.
Right. Well, find it or
There we go.
declare it.
There's the point. Warning just says your source was ambiguous. Now, you want to get rid of warnings. Unfortunately, I can tell you there's a lot of pressure. Oh, you got executable code, go ahead and run it. No. You want to get rid of warnings because warnings means it might work. Doesn't mean it will always work. Doesn't mean it's going to work as soon as it leaves, as soon as it's in the customer's hand.
All you really know is it compiled.
All you really know is it compiled. So, you want to get rid of warnings. Warnings are ambiguities. They at least allow you to keep testing. Now, if you, sometimes you want to enforce that, you can, as one of the GCC options, tell it, make all warnings errors. As soon as there's a warning, don't produce executable code. Okay, so we already got somebody who said a cure. So let's do that. Okay. And all we gotta do is repeat the command. And what do you know? No error this time. Now, the advantage of a toolchain. Try doing that with a binary editor. I have. Not in 30 years, but I have. Actually, I take that back. About 2 years ago, a problem with a microprocessor embedded thing, I actually ended up editing binary in machine. I forget which code it was.
So how big is your binary?
Pardon me?
How big is your binary that you just created?
Well, 2K maybe?
Do an LS, Strauss.
Oh, I'm sorry, I thought you meant the one I...
Oh, no, the one you handcrafted.
Oh, this one, yeah.
That was probably pretty big. It's probably got the symbol table and
Yeah, this one on it.
all kinds of stuff.
12K.
Yeah.
Now, I didn't turn on the symbol table. What he's referring to is one of the options that you can do with GCC is turn on a symbol table.
Turn on or turn off?
Pardon me?
Okay. Well, there's,
Yeah. Now that...
that's got the debugging information in it, but there's a,
okay, it only went up by about 500 bytes.
yeah. Strip it, it'll be much smaller.
Okay, let's try that. Again, another tool out of the GNU Toolchain. Strip. Okay, that cut it to half size, 6,000. Now, one advantage, what's an advantage besides size, which is actually going to be more pronounced on something smaller? What's an advantage to stripping? Yes? Oh, go ahead.
It was back when we were doing debug stuff. I was gonna ask you about lots of debugging stuff in there with GGDB3.
Yeah.
Okay, let's try that.
Yeah, that'll give you, that'll practically embed the source code if you want it.
Let's see if I remember the option on that.
Yeah, it does make debugging easier.
Okay, this is going through the docs, but do you remember what the syntax is for that?
It should just be -GGDB3. Oh, all lowercase, all one.
There we go. Okay.
All one word.
Yeah, just GGDB3.
Okay. Okay, there we go.
Yeah, we'll figure it out.
Yeah, about 3 times.
Yeah.
Okay. I don't know if I got readelf on this machine. Oh, what do you know I do? Oh. Doesn't like it directly. What's the...
Dash
Okay, there we go.
Oh, yeah.
This is, if you need the full information on an executable, this is where you can find it. GNU is very good about giving you lots and lots of information, and in ways that you can search it. Printf, for instance, we had to add it. All right, let's see how that actually got included. Should be in here. Ah, it's not in here,
Passed
surprisingly.
it?
Go ahead.
We passed it already?
Wouldn't think so.
Wow.
That surprises me.
Printf's probably a macro,
True,
right? So it turns into something.
true, but I would have expected it, because printf, I believe, is the system, the group 3 instruction. Let's see, group minus I. Well,
Yeah.
okay. Slightly more complicated.
Yeah, maybe.
So we got a clean source, we tested it, it worked. Slight complication, go to a library. And, okay, by the way, for those who said you hadn't used GNU before, are you following along? Am I going too fast for those who haven't used the GNU Toolchain before? I'm going too fast?
Doing well.
All right. If you got questions, stop us.
Yeah.
Because the experts here have seen this, done this, probably within the last day. All right, so we got another program. This time, by the way, we remembered the include. And anybody want to guess what zlib's for?
Compression.
Compression, right. And again, how many lines do you figure this is?
Including the include?
Including the include and the comments. Have to include the comments.
Oh, just go. Yeah, word count function to do that.
35?
About that. Yeah. So, not much longer, but a little longer.
Yeah.
All right. Oh, by the way, I mentioned the doxygen before. You'll notice this one, take a look here at the, see if I can scan it there. Okay, that's an example of doxygen's input. The /$ tells C that it's a comment. It can ignore, the GCC compiler can ignore it, but doxygen reads this. And it tells it about the corresponding function that follows. Doxygen, I said, it's not actually in the GNU Toolchain, but associated with it. Handles functions, it handles objects, it handles, i.e. class definitions, declarations, usages. So it's a good tool worth looking into. And you actually can use it to do very, very, very stylized presentation, slideshow type. It's actually not bad for, if you, all you want to do is outline type stuff, it's actually not bad. Okay, so, same thing as we did before, let's copy this. Now, anything noticed missing from this program compared to hello.c? Yes,
Doesn't have a main.
doesn't have a main. Okay, so Can you run a program without a main?
Run it, it ain't gonna do nothing.
Technically you can, but it's hard because the ANSI spec says that the nominal entry has to be main. So you can run it with some tools where you tell it to start off at a different function, but you're no longer in ANSI when you do that. So let's supply with a main. Okay. Once again, we said we're changing, we're adding one, all we're doing is very simply, we're adding one more file, so we could have added libraries, we're adding a source code, we could add an object file, we could add a library. Have lots of choices. Zhead. Anybody want to guess what zhead is going to do?
Compress the first few lines and show it.
Ah, there we go. Pardon me?
Uncompress the first few lines and show it.
That's exactly what it's going to do. Now, once again, anybody notice that something was missing before I tried executing it with the toolchain?
The library.
Right. Need a library, but though I had mentioned it this time in the include, I didn't actually tell it where to find it. So, undefined reference. That's not coming out of the compiler, coming out of the linker. Remember we said about the index? It went searching through its index, it found it needed GZ open, didn't find it in any of the libraries given, so complains. And right, all we have to do, turns out, is tell it where to find it. And zlib is nicely available, supplied by GNU, as -LZ. Once again, we're nice and clean build, and we can test it. Whoops. Oops. Where'd my file go to? In case anybody's interested, by the way, the original file on that is not quite so easily read. Simply compressed, not encrypted, just compressed. I assume everybody, well, anybody here not know the difference between encrypted and compressed? Okay.
Difference between encrypted and compressed?
Yes. You can't read an encrypted file, but most people can't read a compressed file either.
Yeah, but the algorithm is published and known and not secret, and so.
Well, the algorithm for encrypted files is published and known.
If you
The
know
difference
the
is
key.
that, and the difference is a compressed file or an obscured file, you can read without a password or without some key, which means that anybody can read it. An encrypted file depends on a key. Either whether it be a secret key, a private key, but it depends on the key. So that only those people possessing the key can read an encrypted file. Compressed file, anybody can read. So
Encrypting doesn't necessarily reduce the size of the file.
not necessarily, but it usually does, because if you don't do a compression before you do an encryption, you retain redundancy in the file that can be used to defeat the encryption. This is how they, if any of you saw the movie The Identity Game or read the book Innovators, 2014 Prentice Hall, they got their dates wrong in the movie and got the bit stuff. But the British had broken the German Enigma machine used prior to World War II. Mostly because they were not using it properly. The Enigma machine was used by, everybody here knows what the Enigma machine is from that movie or from other references? Okay, all but one. Okay, the Enigma machine was a popular typewriter-like machine used in the first half of the 20th century, very popular in Europe. Basically, it was just like a typewriter, but as you type things, it would put a different letter on the paper than what you typed. And it would change via these wheels that were rotating what letter it put on it. So you would start it off with a key phrase, a setting of the wheels, and then as you typed, it would type the message. When it got to the other end, they could, I think, type it in the same letters, and it would then convert it back to the correct, what it originally was. The problem was that the Germans, and it was being used by a lot of companies, not just the German military, very popular, they were sending the same messages multiple times using the same key, starting their messages off with the standard format as the way they presented it in the movie. And this, when you do that with the algorithms called the idea algorithm, you change it from something that is, as far as I know, the only published non-breakable coding scheme, in the sense that you can't do any better than brute force attack. But if you reuse the same key for the same, reuse a key or resend the same message, it becomes a jigsaw-like puzzle called a cryptoquote. They publish a cryptoquote in the daily newspaper. They're fun. So the Germans, the British had broken their Enigma machine prior to World War II. At the start of World War II, the German High Command cracked down on their officers, and it wasn't until the Americans captured a submarine that the British reestablished their ability to read the German encrypted traffic. We got the code book out of the submarine. And the submarine you can now visit, by the way, at the Chicago Museum of Science and Industry. Okay, so that's that. So normally, though, you will, but as a consequence, you will almost always compress any message before you encrypt it. Otherwise, you've largely defeated your encryption. Okay. Okay, so we're in the zhead. Okay, good. We're getting back on time here. So, makefile, another part of the GNU, mentioned it before. Now, anybody, okay, who here has not used a makefile? By show of hands. Who has not? So everybody's used a makefile? Even ones who haven't done, so those of you who said you hadn't done GCC before, or GNU Toolchain, what were you using make for? Anybody?
Compiled something from source.
Compile something from source, but not with GCC?
Not like writing the makefile myself, right?
Okay, well.
They probably called GCC the makefile in a lot of cases.
Right, likely did, because make's part of the GNU Toolchain. You don't have to use it for GCC, you can use it for a lot of things. In particular, I'm sorry, go ahead.
We use it to alias really long commands all the time.
There you go. Use it to generate long commands, right? Okay, so the makefile uses a set of symbols to express dependencies. At the top, conventionally, doesn't have to be, but by convention, there we go. You define for convenience standard set of options on the programs you're using. GCC minus C minus GO is to the same C compiler minus C was don't generate the executable, just go to object. G is put the debugging information in, and O is specify an output. GCC minus O acts as your loader. So it just, for make purposes, it makes it easy to use it to generate all your objects, and only then do the linking to generate your executable. That way, if you have lots of objects, which is common, and you only change one source, you don't recompile every source, you only recompile the ones you know you changed. And unlike me, at least, who can make changes and forget I made them and then wonder why the changes don't show up in the executable, make can tell which files have changed, which files are newer than the object. So it'll make all the source codes I changed even if I don't remember it. That's one of the big advantages of using make. You also have what are called rules. Rules are where you specify a pattern. By the way, these, so far, anything I'm mentioning in this is actually specified by POSIX, a Unix standard. Make implements it. Make has also, the GNU Toolchain has some extensions, but it is very ANSI compatible, which is a big advantage. If you write once, run it on multiple platforms. Okay, most of the extensions that are available give you better performance, but they only do so usually they do so until they break some characteristic of a particular architecture. Or time passes and everybody adopts that better architecture and then it breaks on everybody's. Okay, rule is a pattern. And notice I put the CC in there so I didn't have to put the program with its options all the time. The little symbols beginning with the $sign makes macros. So that this one rule can be used to compile any object, and I don't have to write that script for all of the different source codes. I just write the pattern once and tell make, go ahead and use it. And it's a lot less error prone than I am. And then you got the targets. Targets are where you actually can specify the peculiarities of what you're building. I put help as the first target in here because by default, if you give the first target in make has a special feature, it's the one that make will execute if you don't tell it which target to execute. So it's always a good idea to make your help menu the first target. And make has a pseudo directory structure like algorithm, so that you can group your targets for easy maintenance, easy handling, automatic production with the preprocessor. There are large systems called xmake and makemake that take advantage of that to manage large projects across multiple platforms. I don't know if it's still true. One of the X's, I think it was XF86, and I don't know if it applies to XOR. Its source code was managed with xmake, which is make, I think with the GCC preprocessor. Okay. And GNU has a standard set of targets. It's a convention, it's not, you're not obligated. But they developed a standard set of targets that's now followed by a great many people. The GNU Toolchain, one of its it's been so popular, it has set a lot of the standards. Okay, so quick demo. First, no arguments, and the make file found. Well, there we go. Okay, no arguments, tells you how to use it. Let's give it real clean, and one nice, it'll show you what it's going to do here. Okay, it's going to remove the executables, and apparently there aren't any objects since it didn't say it was going to remove them. Yep, there aren't any. Okay. Oops. Okay. Now there's no executables there. Now we can, for instance, say make all. Make all was a generic target, which in turn is going to make the two executables, flow and zhead. You can hierarchically program make. It's you don't have to, but it makes things a lot easier. So let's make them all. Now we got new versions. One runs. There we go.
Runs.
And I don't think I have a test in here. Oh, okay. I normally like to add a test target with make so I can run all my tests as well. And if I just wanted to build one, could do something like, for instance, make zhead test, and I can just test one of them. That's that pseudo directory structure. Again, it's a convention, it's not mandated, but GNU established, again, tend to establish the things. Okay, so further, some we haven't mentioned, GNU Toolchain has GDB. This is for debugging. It allows you to step through the source code that you have, both C, C++, Fortran, Java, etc. Autoconf. Autoconf, assuming those standard targets in the make, allows you to set up a standard build scripts. M4. M4 is substitution. What it allows you to do is write files as a template and then provide it with variables. The classic example of this, which would be your, I know nobody does this anymore, but Christmas cards. You write a standard letter, you want to personalize it for everybody. You could, M4 is you would write a template and then provide it with a flat database, everybody's name, how to address them, whatever, and it will generate all the different address labels, cards, etc. Okay, bison+flex. If you want something beyond what is already standard, ANSI standard, GCC, etc., you can write your own parsers. Perl was created as the portable extraction and report language, which is another way of saying it was supposed to be a compiler. Almost nobody used it for that. Bison and flex are tools for doing that. So you got your own custom language. Your company has its own way of writing messages or writing some kind of script. Bison and flex can reduce the anything if it's repetitive, you can turn it into a compiler. Okay, lots of documentation. Man pages came out of AT&T, and they were standard because originally the docs that got distributed were with info, which is a hierarchical compressed form. Very good when you're short on memory. But every time you made a change, you had to edit everything. You had to recompile the whole system. Man came along with easily indexed, searchable documentation. And ironically, GNU went back to info. They've been pushing info. They have made it, however, far, far easier to make updates. You can do incremental updates with it, which makes it a lot more practical. And they supply, and okay, of course, today we've got Google Stack Overflow, Linux documentation. Design tools we mentioned, doxygen, plantuml, yes.
You have 5 minutes.
5 minutes. Good. I got it timed almost perfectly then.
Yeah.
Okay. plantuml is a diagram tool. Again, it's not part of the GNU Toolchain, but it fits very well with it. It is used for generating UML documents in a doxygen style, i.e. you write source code that gets converted into UML diagrams. Is there anybody here who does know what a UML diagram is? Uniform Modeling Language. One person. Okay. Do you know what flowcharts are? Okay, good. Flowcharts were an IBM standard from the 60s, a way of, we are visual animals. It was a way of visually representing algorithms and other information. With object-oriented programming, however, flowcharts, which assume a single thread, aren't as easy to represent in a flowchart. And so there were lots of, every different company in the world developed their own graphic system for it back in the 70s and 80s. So, and every textbook was different. So I think it was ISO, it was one of the European standards organizations, I think it was ISO, anybody can correct me if I'm wrong, got together a committee and they said, this is the way we're going to do it. Arrows go from their dependencies back to what they derive from. Filled-in arrows means that on the filled-in side, it is fully transferred over to the non-arrow side. An open triangle means that it's partially transferred, and so on. They just picked some arbitrary choices, since everybody else had, if there were two companies, they always picked the opposite. So with UML, it's one set, and at this point, I think it's becoming most popular. Is there anybody using object-oriented diagrams that are not UML? Nobody? Okay, well good, then UML. So Plant UML is a source code from textual fields generates UML. Okay? All right, integrated environments. Emacs electric mode, Eclipse. How many people here are using Eclipse? 3, 4, okay. How many people are using Emacs IDE? Okay, 1. How many people using some other IDE? 1. Okay, I recommend IDEs. They save you a lot of time and trouble, but I will warn you. When you use an IDE, make sure that you can still compile your code, build it completely without it, because otherwise you tend to lock yourself in and end up, especially when you have to change, somebody adds a new platform, a new environment. So, and it's usually just a matter of care. Okay, decompilation. These are part of GNU. readelf, I think that's part of GNU. This allows you to deconstruct the object files, the libraries, the executables, and when you have to debug them. strace, I think that's GNU. It allows you to monitor all the system calls that they make. Again, for debugging.
Ltrace is very handy too.
Ltrace, okay, and Ltrace, go ahead, describe it.
Oh, it's like strace, only it's not for system calls, it's just for library calls.
There you go, Ltrace for library calls.
Library calls that don't involve calling the system.
Okay. So, GNU Toolchain, you can compile the standards ANSI. It's been around for 30 years. By this time, I think it works. Very reliably, very portable. Works on, I haven't met a platform it hasn't worked on in about 15, 20 years. And code compiled in one. I didn't think it's been 5 years since the last time, probably longer than that, since the last time I compiled code for one platform and couldn't compile the exact same source code for another platform, assuming I stuck with the ANSI standard. All right, any questions, expansions, comments? Are you all?
I have one question.
Go ahead, lots of questions.
Bit of a lower level than some of the conversation was about, but specifically about if you have like a program that is working great at the beginning and slows down over time, potentially memory leakage, or other kind of standard tools, can you try monitoring those things?
Can you say it a little louder?
Resource monitoring. So your memory just
looking for
mentioned
memory
all
leaks.
these-
Well, there's two things. There's gprofile, which is part of GNU, and what it will do is it will modify, keep me honest on this one, because I haven't used gprofile in a while. I believe it modifies the binary code to put in traces, start of entry of functions, exit of functions, other places. And so it looks for timing. It also does some limited memory checking. In other words, when you enter a function, it tries to keep track of the stack, which in turn tells us one major source of memory leaks. There is another tool called Valgrind, which I'm not sure if that's in the GNU Toolchain or not, but it's definitely associated with it. And Valgrind is very good at finding memory leaks. It will basically monitor images. You can also use in GDB, there are what are called watch commands. The watch commands insert temporary code, in other words, it actually inserts it into the running code, to do branches when upon memory or other state changes. So you can use it to find where you're overwriting memory, where performance is failing. Would that help you?
Yeah.
Okay, so Valgrind, gprofile, GDB. Other questions? Okay. Thank you.
Thank you.
Just a quick reminder, we do